Okay, welcome back to class, everyone. Good morning. Let's see here. It is the 12th of September. We're right on track with everything. We've been talking about the normal distribution. We noticed that if you look at the null distribution for the sample proportion, that it forms this curve, right? And the bell-shaped curve, and we call that the normal distribution. So we're working through the properties of the normal distribution, and it'll give us a lot of power in doing more hypothesis testing soon enough, pretty soon. So are there any questions? You guys have any questions you want to go over? Anything from the homework you want to ask me? No? Okay. So let's get back into what we're doing then. Let's see. We were here on page 69, and we were practicing with using GeoGebra to find area under the curve. Okay, and the reason we care about that is because it helps us understand our distribution better, right? So let's do one more of these. Let's say we want to find the area under the standard normal curve between z equals negative 0.85 and z equals 1.3. So let's draw that. It always helps to have a nice sketch. And on the exam, sometimes I'll require that you draw a sketch for points. So just make sure you're practicing with drawing that when you're doing the homework. So if it's the standard normal curve, then we know that the standard deviation is 1. So that would be about negative 1 right there. So negative 0.85 is going to be a little bit to the right of that. It's a little bit more than negative 1. So that would be negative 0.85. And then if we go out to the right, one standard deviation, that takes us to the inflection point. That might be about right there. So 1.3 would be just a little bit to the right of that. Okay. And by using those inflection points, I can give myself a pretty good idea of what the final answer is going to be. So it gives me a sense check. It helps me make sure, I'm thinking about this the right way. And so, yeah, there's 1.3. There's negative 0.85. So what does that area look like to you? I mean, if you just had to guess, if I had to guess, I would probably say about 60%, right? I mean, it does look like more than half of the distribution is between those two values. 60, 55, somewhere in there. It's hard to do much better than that with guessing, but we don't have to guess exactly, right? We can go to GeoGebra and it will tell us exactly the area between those two values, right? So let's remind ourselves how this works. So we go to the toggle, the 3 dots, probability calculator. We're in the standard normal, so mu is 0, standard deviation is 1. And now we want between two values. So there's a number of options here with the GeoGebra. We want the between. And so it was between negative 0.85 and 1.3. Okay, so notice that's the same picture that I drew over here. Theirs is, of course, a little bit better because it's software, but everything's lining up. It's what we're expecting. And it turns out the area was a little bit more than I guessed. It's about 71%, 0.7055, but it's still very much in line with what I was expecting. So 0.755, 0.7055. So about 71% of your distribution will have a z-score between negative 0.85 and positive 1.3. All right, let's keep going. So there are times when in kind of the real world, people will use z-scores. I think I mentioned that there were recently on a couple of ultrasounds that we had done, they actually printed z-scores on there. But most of the time, when you're out in the real world and you're not doing like theoretical statistics, when people are using the normal distribution, they're probably not going to use the z-score, or they might, but it's a little bit more common to avoid the standard normal and just go with a typical normal distribution. So there was an example in the book. If you're reading the book, great. If you're not reading the book, I recommend that you read the book. This is from section 3.2.4 in the textbook. And they were talking about SAT scores. So you're probably aware of this, but maybe not. The SAT is one of those standardized exams that typically people take towards the end of high school, and then depending on that score they get on that exam, they can apply for certain colleges, right? So it's pretty well known that SAT scores are approximately normal, with a mean of 1100 and a standard deviation of 200. By the way, this notation, I haven't really talked about this notation very much. Every normal distribution has a mean and a standard deviation. So if you don't use a notation like this, then you have to write that out. You have to say normal distribution with mean this, standard deviation this, and that's a lot of writing. So instead, what we can do is we can say capital N, that tells us normal distribution, and then the first number is the mean, and the second number is the standard deviation. So with just those, that's that compact notation, I can tell people, hey, this is a normal distribution. The mean is 1100. So that's like the average score for SAT scores. And then not everybody gets the same SAT score, right? Of course, some people get higher, some people get lower. So there's spread in the population. And we measure that spread with this standard deviation, sigma, right? So the average spread there is about 200 in those SAT scores. So in 3.2.4 of the text, we were looking at Shannon's z-score. She had a z-score of 0.45. And if you read that example, it says that the probability that somebody would get higher than 1190 on the SAT was this value here. And I'm going to pretend like we can't see it, okay? Because I want to confirm that that's the right number, right? So let's just pretend like we don't know it. My question is, what is the probability of getting above Shannon's score? So we're going to take one randomly selected SAT test taker, and what's the probability that they got higher than Shannon? Okay, so Shannon's score was 1190. So what is her z-score? So let's calculate the z-score. So remember, the z-score formula is x minus mu divided by sigma. So it tells us the number of standard deviations away from the mean we are. Okay, so or the number of standard deviations above the mean. Okay, so x is the observed measured score. So that's Shannon's score. Mu is the mean for the population. That's known to be, it's published to be 1100. And then sigma, 200, right? So we pull out the calculator and we confirm quickly, okay, 1190 minus 1100. Okay, then we divide that by 200. And we know, and we've confirmed what we already know it to be, right? 0.45, right? So we're just kind of confirming that number there, right? So the z-score here is 0.45. So now that we know Shannon's z-score, we can find the percent of the distribution that's above that z-score. Okay, so you imagine the z-score, the z distribution, right? The standard normal. So we have 0 there in the middle, symmetric about 0. Then maybe that's the inflection point out there. So 0.45 is about right here. So it didn't ask us to do this, but won't hurt at all to shade that in. That's the percent of students who score higher than Shannon. So she's above average, and so it'll be less than 50%. What is the percent? Okay, so guess, based on my very rough sketch here, I would probably say, 30, 40%, right? But we don't need to guess because we have GeoGebra. Okay, so what button do we select? Well, this is a right tail test. I'm sorry, this is right tail of the distribution, right? It's greater than, right? Scores above, yep. The mean here is 0, standard deviation is 1 because we've done the z-score, so we've converted it over to the standard normal distribution. Okay, so we're looking for a probability. So probabilities are on the outside, right? Probabilities appear over here, or our input output over there, and then z-scores are input output in there, right? So what's the probability of getting a randomly selected student who has a z-score above 0.45? That's what we're going to do, but in GeoGebra. Okay, so we go greater than 0.45, and there we go. It's 0.3264. Okay, so that picture actually looks pretty close to what I've drawn here. So, it sounds right. It seems reasonable, and it's about 33%. So 0.3264. So that's what appears over here, 0.3264. Okay, now, if you were playing around with GeoGebra last time, and especially if you've maybe done some homework, you might have asked yourself, well, can't I alter, is it possible to alter the mean and the standard deviation, for example? Yes. Okay, so by doing that, you change the center and the spread in the normal distribution. It's still normal, but it has a different center and it has a different spread. And that makes sense, right? Because let's say you're using the normal distribution to think about weight of adult females, right? So adult females will have a certain average weight. That'll be the middle of the distribution. But you might use a different normal to look at the weight of newborn baby males, right? So that obviously they would have a different center, right, and a different spread. So that's what sigma and mu do for us. They allow us to look at all sorts of different normal distributions. For example, if we have one with mean 1100 and sigma equals 200, okay, so we can actually, in some cases, bypass the z-score and go directly to the relevant normal distribution. Okay, so instead of calculating a z-score, in this case anyway, we can sort of bypass that. So do you see how by putting in 1100, it's changed the location, right? The peak is now over 1100, and the distance from the center to the inflection point is now 200, right? So it's much wider than it was, and it's shifted way out to 1100. Okay, so then we're going to go greater than, and Shannon's score was 1190, and what do we see? 0.3264. Okay, so it's just a little bit easier sometimes to bypass the z-score. Sometimes we need the z-score. The z-score is sort of the part of the core theory of stats. So a lot of the formulas are written in terms of z-scores. So we never get away from them entirely, but sometimes we can kind of bypass the z-score a little bit. And that's nice. Okay, so 0.3264. So let's write that down. Okay, so 0.3264, and that's for 1100, 200, and then greater than 1190. Okay, so notice the answer is the same, but the second way is a little bit faster, right? Because we didn't have to calculate a z-score. All right. Let me do one more, and then I'd like you guys to try one. Yeah. Okay, so instead of SAT scores, let's look at heights of adult males. Okay, so height it does tend to be roughly normally distributed. And so what we'll do is we'll look at men who are kind of in their peak, physically at their peak, right? So, after your 60s or so, you'll probably tend to start losing some height. So between 20 and 62, you're pretty much your adult height, right? So so the mean there is 70 inches. Okay, so we'd say mu equals 70 inches. But not everybody's the same height, obviously. Some people are shorter, some people are taller. So there's spread in the population, and we measure that spread with standard deviation, with sigma. So the sigma here is 3.3 inches. So your typical person is about 3.3 inches, within 3.3 inches of the average. So if you're reading the book in 3.2.4, we found the probability of a random male being between 5'9" and 6'2" to be some value. Now I've kind of covered it up. I'll just pretend like we can't see it for a second so we can, so, you know, we know what we're trying to find, right? So, so if somebody comes to you and says, what proportion of males are between 5'9" and 6'2", then you can find it with GeoGebra. Okay, so one thing you have to do, the foot and inch measurement is kind of a mixture of two units, right? We have feet and we have inches. So it's probably best if we switch it over to inches over here. So for example, if you're 5'9", then you are 5 feet plus 9 inches. So if you're 5 feet, you're 5 times 12 inches, right? Each foot has 12 inches. So if you have 5 of those feet, you are 60 inches plus 9 inches. So you are 69 inches tall if you're 5'9", right? So you have to do the same for 6'2". Then you use your between two values, right? So you can go right to GeoGebra. You can skip your z-score. If you want to challenge yourself and calculate z-scores, you can, but it's more work than necessary here. Okay, so I'll go quiet for a couple minutes and let you guys work with this. Let me just give you a couple more hints here. That would be 70. That would be 3.3. This makes sense? So give it a try. I'll go quiet here for just a minute and let you work on this. What percent of males are between 5'9" and 6'2", adult males? Anybody get it? So let's see.
I got
Yeah. What'd you get?
0.5. Is that right or no?
Yeah. Yeah. Could you round it maybe to like the third or fourth decimal place?
Yeah, so it'd be 0.5063.
Perfect. Yep, exactly. So yeah, 5'9" means 69 inches, and then 6'2" is 74 inches, right? So if you're 6'2", then that's 6 times 12 plus 2 inches. So that's 70, 2 plus 2 for 74 inches. Okay, so great. So that's the between two values. And so we run over to GeoGebra here. This is a totally different normal distribution. So we're going to go 70, and then we put in the average spread there is 3.3. Then we go between two values, 69 to 74. And we have a 0.5063. By the way, my guess is some of you have a slightly different looking number there, maybe because of rounding. So for rounding, if your number does look a little bit weird, then hit this gear here on the left and then the gear on the right, and then you can tell it what to round to. And I usually try to get mine rounded to lots and lots of extra places of accuracy. It's a little bit unsightly, but you get more information sometimes. So you can see here, rounded to 15 decimal places, what that answer is. Okay, so good. All right. So obviously that's quite useful, right? If you're a researcher, you're trying to understand a population, now you can actually segment the population pretty nicely, right? So you can create segments, and it's super useful. Okay, what about going in reverse? Okay, so what we've done here is we've taken values in the distribution, actual heights, and we've found proportions, areas, probabilities. But what if we want to go in the reverse direction? The reverse direction is called the percentile problem. Okay, so when you're finding a percentile, let's say you want to find the 10th percentile. The 10th percentile is the value in the distribution such that 10% is below it. So with the percentile problem, it's related to what we were just doing, but it's kind of like the exact opposite. Okay, it's like 90% the same thing, but 100% totally the opposite. All right, so what am I talking about? Well, let's look at this one right here. Okay, so we've got Eric. Eric is at the 40th percentile for height. Okay, so he's a little bit short, but not super short. He's still taller than 40% of the population. So if you're reading the book, it was shown that his height was that. I'm going to cover it up for a second. And so basically what we want to find is the 40th percentile for men's heights. Okay, so we're looking at adult males, and we want to find the 40th percentile for adult males. So how do we do that? Well, it's quite easy with GeoGebra. If you're using the table, you can still do it, but it's a little more work. So as I've said before, we can put away the table and just use GeoGebra. So how does it work in GeoGebra? It's very easy. Okay, so we put in the mean and the standard deviation. So it's the same population, 70 inches for the height, 3.3 for the standard deviation. And then if it's the 40th percentile, we know that 40% will be below, right? So we're going to go below. And then remember, with the way GeoGebra is set up, areas, percentages, proportions, probabilities, these are the numbers that are input or output on the outside. Values in the distribution are input or output on the inside. Okay, so 40% is 40%, right? It's a proportion of 0.4. So what we'll do with GeoGebra, up until now, we've been putting in numbers over here and getting numbers over here, right? But now it's the reverse. We're going to put numbers in over here, and it's going to output numbers over here. Just watch. It's very easy. Okay, so same distribution, 70 and 3.3. So I'm going to go less than because it's the 40th percentile. We put in 0.4, and there we go. There's his height, 69.2 inches. Okay, so we go 69.2 inches. Now, whenever somebody asks me my height, I always say like, to the nearest whole inch, typically, right? You might get some people who says like, they might use like a half inch or something, but I've never heard anybody in casual conversation say, I'm 0.2 inches or something like that, right? So yeah, 69 inches, as we just saw, is 5'9", right? So Eric's height is 5'9", which is what we showed in that example in the text, right? Okay, so in other words, the 40th percentile for adult male heights is 5'9". Okay, so what do you guys think? So you try one. Okay, so let's take this kind of abstract example here, where we have a mean of 22.8 and sigma 5.4. What value will have 10% more than it? In other words, what is well, if 10% is more than that value, then 90% of the distribution is below it. So what is that? This is equivalent to the 90th percentile. So it's just another way of asking, what is the 90th percentile? So go ahead and see if you can do that with GeoGebra. And then we're going to do lots and lots more practice, okay, until you're comfortable with using GeoGebra to work with the normal distribution. Very, very, very useful distribution, and it's just always just right around the corner whenever you're doing statistics. It's ubiquitous for sure. Okay. As soon as you get it, just put the number over in the chat or speak out loud. It's perfectly fine. All right. Thank you, Brock. It is 29.7. Very good. Yep. All right. So how do we do it? Well, we put in the mean, put in the standard deviation, which is sigma. If you want 10% less than, you can go, you hit the less than button, and then we put in the probability over there, 0.1, and then it's going to output the answer right there. Okay, so let's do that. So we have less than, and we need to change the mean and the standard deviation. So this is 22.8, 5.4. Then we're going to go less than. We want that area to be 0.1, right? So, sorry, we want, hold on. We want 10% more than, my mistake, sorry. Sorry for messing that up. We want 10% more than, right? So we get 29.72, as Brock said. Great. So I actually circled the wrong thing over here. My apologies. It's 10% more than. Good. Okay, so there we go. Any questions about that? Sorry for goofing that up a little bit. So 29.7. Well, if that makes sense to you, then let's jump into some more exercises here. Just so we're all super comfortable here with this. So on the next 2 pages, there's 4 different exercises. They're all kind of doing the same thing. So I think what we'll do is maybe 2 of the exercises. I don't think we need to do all 4. It kind of takes a lot of time. So I'll do this one. Okay, so let's say we've got this bag of chips here, a bag of chocolate chip cookies, and we're going to answer some questions. Why? Well, it's like quality control. Chips Ahoy is a huge company, and they want to make sure their products are good. So they do monitor how many chocolate chips are in their cookies. I promise you, they have a spreadsheet, they have a target number, and they collect data on it. They do sampling, and they make sure their machines are working correctly. Okay, so the target is 1,262 chips in one 18-ounce bag. But nobody's going to complain if there's, like 5 extra chips or 5 too few chips, right? Nobody would know because people don't count when they're eating. But if there's like 500 chips, then, people would notice and they would complain about that, right? So so what they do is they have a target for the spread there. Okay, and so the target is 118 chips. So your typical bag will be about 1,262 chips right in the middle there. But there is some variation. And they're okay with this kind of variation here. Why? Because as long as it's, within that value or so, customers won't really notice or care, right? So it's just considered, good standard quality as long as it's, kind of within that range. Okay, so that's the goal. That's how we know if the machine's working. So what we're going to do is we're going to practice with the inflection point. You can't practice enough with that. So I'm going to go 1262 plus 118. So that'll give me 1380. Then I'm going to go 1262 minus 118. That'll be 1144. Then, just for good measure, I'm going to go another standard deviation out. So now I'm 2 standard deviations out. And so I'm going to add another 118. So that's going to be 1498. And then if I go 1144 minus 118, that's 1026. I like to do that because it gives me an idea of the distribution. Okay, so by the time we get to 1026 chips, it's getting a little bit weird, right? We're 2 standard deviations below the mean. And, perhaps there's an upper limit to how many chocolate chips we want to have in there too, right? Maybe at some point it just becomes kind of too much, right? So 2 standard deviations above would be 1498. Okay, so that by doing that, I can give myself a nice sense check for how the distribution is laid out. Okay, and then I can answer these questions a little bit more comfortably, confidently. So what is the probability the randomly selected 18-ounce bag contains between 1,000 and 1,400 chocolate chips? So where is 1,000? 1,000 is below 1,026. So 1,000 would be like right here, right? So I'm going to shade in that region. So we start at 1,000, which is way down in the tail, and we're going to go up to 1,400. 1,400 is about right there. Okay, so I want you to get in the habit of shading the relevant area of the distribution. You guys see 1,400 about right there? Okay, and then 1,000 would go, almost all the way down, to where we can't even see in the left tail. So what does that area look like? Okay, what's the probability of being between 1,000 and 1,400 chips? Well, that's the vast majority of the bags of chips, right? The vast majority are going to be between 1,000 and 1,400, as we can just see from our diagram there. So what does that look like to you guys? Maybe 80%, 90%? It's very high, right? So my guess would maybe be about 85%. But we don't need to guess, right? We can go to GeoGebra and do that. Okay, so we run over to GeoGebra. We put in the mean. It's 1262. We put in the standard deviation, 118. And then we're going to go between two values, right? So the lower value for this first part A, was 1,000 up to 1,400. And yeah, I guessed about 85%. And yeah, it's like 87%. Okay, so the vast majority, or 87%, of these bags of chocolate chip cookies will have between 1,000 and 1,400 chips. So 0.8657. Okay, so 0.8657. Now, that's kind of a long sentence to write out. What is the probability that randomly selected is between, so if there is a notation for working with probabilities that can speed up communication a little bit. And the way it goes is this. You have a capital P, and that says probability. The P stands for probability. And then the parenthesis is of. So the probability of some event. Okay, so what's the event? Well, that our value is greater than or equal to 1,000 and simultaneously less than or equal to 1,400. So what is the value? Well, we don't know what it is, right? It's kind of a variable, so we'll call it x. So in other words, what's the probability that our quantity of chocolate chips is between 1,000 and 1,400? See that notation? So it's a much faster and probably more accurate, precise way of saying that sentence. Okay, so take it or leave it, that notation. I'm not going to require you use it, but I do use it a lot. So just be aware of how it works. All right, so that's A. Let me do a couple more of these. What's the probability that a randomly selected bag contains fewer than 1,000 chips? Okay, so I'm going to come back up here to my diagram that I had a nice looking diagram, and then I kind of messed it all up here. Okay, so here it says, what is the probability that a randomly selected bag contains fewer than 1,000 chips? Well, look up here in my distribution. 1,026 is already way down in the left end of the distribution. 1,000 would be even further down there, right? So if you're shading that in, it would almost be imperceptible, right? There's 1,000 way down here. What's the probability that a randomly selected bag has fewer than 1,000 chips? Well, the distribution does extend down there, so it's possible there's a bag that has fewer than 1,000 chips, but how likely is it? Okay, or in other words, P of X less than or equal to 1,000. What is that probability? Okay, so that's probability of our quantity, the number of chips, being less than or equal to 1,000. Okay, so we don't need to guess. We can ask GeoGebra, right? We go less than 1,000 is a value in the distribution. Okay, and then the proportion, the area, the percentage, the probability, those are the numbers that are output on the outside. So it's 0.013. Okay, so 0.0132 to the fourth decimal place. So what does that mean? About 1% of these bags are going to have fewer than 1,000 chips. Okay, so it will happen eventually, but it's not very common. Just about 1 out of 100 will have that. Okay, and so that happens sometimes, right? I mean, I think we've all, every now and then you just get that bag of candy or whatever snack food. You get it, and it's just off. You can tell that it does happen, but it's not super common. Okay, let me do these other ones, and then I'm going to have you guys try one. So what proportion of 18-ounce bags contain more than 1,200 chips? Okay, so I think you can tell all these questions are just kind of minor variations on the same thing. Where is 1,200? It's about right there, right? It's about halfway between 1144 and 1262. So if that's 1,200, then that's the area above 1,200. I guess if I sort of transpose that picture over here, what does that look like to you? Maybe 60%, maybe 70%, 65%. I mean, we can't really guess that well just by looking at it, but we can have an idea. Certainly more than 50%, probably about 70%. Okay, so on your exam, you'll have to draw a sketch like that. Okay, so get in the habit of making normal distributions. So to answer that, we'll go over to GeoGebra. We're going to go greater than 1,200 is a value in the distribution. And there we go, 0.7004. Okay, so the probability that X is more than 1,200 is right at about 70%. So very likely that you'll get more than 1,200 chocolate chips in your bag of cookies. Okay, it's not for sure, but it's very likely. Okay, I'm sorry. And then D here, there's one slightly new thing here in D. Any questions about any of these? Okay. Let's look at this one here. It says, would it be unusual to select a bag that contains fewer than 900 chips? So we need to have a way of defining unusual. Okay, a good rule of thumb in probability theory is that if the probability of an event is less than 5%, then we call it an unusual event. Okay, so think about you're planning a picnic for your family reunion picnic, right? And so you look at the weather forecast, right? The 7-day forecast for Saturday, and it says there's a 3% chance of rain, right? So you say, well, okay, 3%, that's very, very small probability. So you schedule it, right? And then Saturday you show up and it rains, right? It can happen. There's a 3% chance of it happening, but that's unusual, right? Okay, so So the rule of thumb is if the event has less than a 5% chance of happening, it's considered unusual. Okay, so would it be unusual to get a bag that has fewer than 900 chips? Well, let's look at our distribution up here. Okay, because I've put in the inflection point and another standard deviation, I can tell, 900 is way down there at the very end of the left tail of the distribution, right? So I can make a very safe guess here and just say, yes, that would be unusual. It's such a small proportion. But we don't have to guess because we can use GeoGebra, right? So the probability that X is going to be less than 900, what is that?
That'd be 0.0011.
Perfect. That's exactly right. 0.0011. Excellent. Thank you. So come over here and yep, 0.0011. That's not 1%. That's a tenth of a percent, right? So that's not 1 in 100. That's 1 in 1,000 bags, right? So it will happen. If they, obviously they're producing thousands of these bags, maybe even millions over a long enough time period. So there are bags out there that have fewer than 900 chips probably, but it's very rare. And that's good from the company's perspective, right? They don't want to have a lot of these bags out there that are, kind of defective. So we would say, yes, it's unusual because 0.11% is less than 5%. Okay. All right. So you guys try one. There are two examples on the next page. Like I was saying, there's four examples here. I think two is probably all we need to do in class. Anything more than that would be kind of overkill. Um, let's see. Yeah. So why don't you guys try this one? We have about 40 more minutes here of class. So yeah, let's take about 15 of the 10 or 15 of those minutes, and I want you guys to try this one right here. Why don't we work with the height of American adult women? Okay. So it's distributed almost exactly as a normal distribution. The mean height for adult women is 63.5 inches with a standard deviation of 2.5 inches. Okay. And then so, answer these questions here. A, B, C, D. What's the probability that a randomly selected woman is between 68 and 72 inches, shorter than 70, I'm sorry, taller than 70, shorter than 62? And then this question about being unusual, right? And again, the rule of thumb is about 0.05. Okay, that's the rule for our class. It's not really a golden rule or anything. It's just sort of a it's not etched in stone or anything. It's just sort of a rule of thumb for unusual events. Okay, so I'll go quiet here for about 5 minutes. Let's make it 6 minutes here, and then we'll all come back together and talk about this. I'll open up a chat room if you'd like to chat with some other people about it. So 12:19, let's all come back together in here and talk about this, okay? Okay, let's go through this. So, so 63.5 here in the middle, standard deviation 2.5. So if I start adding 2.5, that'll get us to the inflection point there. That's 66. If I add another 2.5, that gets me to 68.5. If I then start subtracting 2.5 from both sides, that'll get me to my other inflection point on the left, which would be 61. And then if I go one more standard deviation, that's going to give me 58.5. Okay, it's definitely worth your effort to do that, because then you understand the population better. Okay, so between 68 and 72, 68 is over here, and then 72 is much further than that, right? So it's not a huge proportion. Does anybody have it? What is the so if you randomly select one female, what's the probability that the height is more than, I'm sorry, it's between 68 and 72. Sorry, 68 less than or equal to x less than or equal to 72. So we have probability between those two values. Great, you guys got the same thing. So sounds like it's making sense, right? So it's about 3%. So 0.03559. Perfect. Okay, so you got about a 4% chance of selecting a female between 68 and 72 inches. It's pretty tall. It is possible, but not super likely. Okay, what's the probability that you randomly select a female who's 70 inches or taller? Anybody get that one? Where is 70 inches? 70 inches is way out here in the right tail of the distribution. So it can happen, but not very likely. Great, yeah, it's 0.0047. Okay, so if you shade that region, you can barely even see it. It's very small. So x greater than or equal to 70. It's less than 1%. Okay. Anybody have shorter than 62? What's the probability that a randomly selected female is shorter than 62 inches? Let's see here. Great. So you guys are nailing this. Yeah, 62 is about right there. Right? It's more than 61. So that's a substantial part of the distribution. It's not a majority, but at least at least 30%, 20, 30% or so. But we don't need to guess. We can use GeoGebra to get that. So 0.2743. Okay, so yeah, let's do some of these in GeoGebra. Okay, so the mean now is 63.5. The standard deviation is 2.5. And so for the first part, we're trying to get between two values, 68 and 72. So yep, it's about, oh, let's see, did I do something wrong? I messed up something there. Oh, it's 2.5 for the standard deviation. Okay, so yeah, 0.03559. That's part A. So for part B, it says greater than what? 70 inches. So yeah, we can see it's way out here. It is shaded, but it's almost imperceptible. It's about 0.00461. Okay, so less than half of a percent of females are taller than 70 inches. Okay, shorter than 62, so we go less than. And there we go. We get a pretty good chunk of the population is shorter than 62 inches. Not a majority, but more than a quarter. Okay, and then finally, would it be unusual to randomly select a woman who is less than 62 inches? Anybody have that one? Would that be an unusual event? No, because it's more than 5%. Perfect, Armand. Yes, no, not unusual because 0.2743 is more than 5%. It's not unusual. That's would not be unusual at all. Okay, great. So that's all we need with GeoGebra there for working with the normal distribution. What we're going to do now is another another kind of segmentation of a normal distribution. And in some ways, it's not as flexible as using software, but it is kind of nice to have sort of a back of the envelope kind of quick approximation for uh, segmenting your population. And it's another use of standard deviation. So we know what standard deviation is. It's like a measure of how spread out a population is. So we kind of have this idea of what we use it for, but with this rule here, with this segmentation rule, it gives us another way of thinking about how to use the standard deviation. Okay, so in various fields, you take your population and you segment it into different groups, right? So if you're in sales, you might segment based on age or by gender, or all sorts of different kind of characteristics, right? So what we're going to do here is we're going to use standard deviation to help us break the population up into groups, into segments, okay? And so it's quite the name. It's called the 68, 95, 99.7 rule. Okay, so it's not the most elegant name for a rule, but we like that because you kind of like memorize the numbers, right? Many texts will call this the empirical rule. Okay, so it sounds a little bit nicer. Um, so what does it say, and why is it empirical? Well, statisticians, data analysts, been around for a while now, taking statistics and recording data and values. And it's fairly old, at least a few hundred years for people who thought of themselves as using distributions. And so they've had some time to notice patterns in data. And so these patterns were at first kind of empirically discovered. And what they noticed is okay, if you have a bell-shaped curve, of course you have mu in the middle, the mean. And if you start using sigma to break up the population, these three numbers tend to appear over and over again in all sorts of different kinds of distributions, normal distributions. Okay, so what are they? What are these three numbers? Well, what we do is we start in the middle at mu, and we go out one standard deviation to the right. Okay, so that's mu plus sigma. Okay, so mu plus sigma, we know, takes us to the inflection point. So there's our inflection point. If we also then go one standard deviation to the left, that's mu minus sigma, then of course we know that gets us to our other inflection point. And what we notice is that with all normal distributions, we'll have about 68% of the population falling in that segment. Okay, so 68%, that's the strong majority of the middle of the distribution. So 68% of the data will typically fall between one standard deviation to the left and the right of mu. Okay, so it's a segment based on sigma. Then they noticed another pattern, and it went like this. If you go two standard deviations out, okay, so we're going to start at mu, and we're going to go one standard deviation, two standard deviations. That gets us to mu plus 2 sigma. And then if I start at mu in the middle and I go one standard deviation, two standard deviations to the left, we obviously are going to pick up the vast majority of the middle of the data set. It's about 95%. Okay, and this holds true whether you're looking at the normal distribution for heights of newborn babies, or weight for adult giraffes or something, right? So I mean, just for widely ranging populations, these numbers keep appearing. Okay, so that's two standard deviations out. We'll go out two standard deviations, we get 95, the middle 95% of the population. Okay, so that that kind of makes us wonder, well, does the pattern continue? Yes. If you start at mu and you go 1, 2, 3 standard deviations out, then obviously you're going to pick up more of the distribution. And then if we go 1, 2, 3 standard deviations out to the left, we're going to get way out to the left end of the distribution. By that time, we've picked up almost everybody in the population. Not quite everybody. There are some people out there who are extremely tall, or maybe extremely short, or extremely light or extremely heavy. There are people beyond 3 standard deviations, but it's a very small part of the distribution. Okay. So that's called the 68, 95, 99.7 rule. And it's a great way of getting a quick segmentation for your population. So let's practice with one of these, and I think you'll get the hang of it pretty quickly. Okay, so let's do it. So if a distribution is bell-shaped with mu equals 12 and sigma equals 2, approximately what percent of the data is in the following intervals? So anytime I get one of these empirical rule type problems, before I answer any of the questions, I just get my segment set up. Okay, so I go 12 in the middle, plus 2, plus 2, plus 2. 12 in the middle, minus 2, minus 2, minus 2. Okay, so that sets up these tick marks on the x-axis. Right? Then we start applying that rule. So between 10 and 14, well, 10 is here, 14 is over here. So what percent will be between 10 and 14? Well, that's 1 standard deviation in both directions. So there we go, 68%. What percent will be less than 8 or greater than 16? So less than 8, where is 8? 8 is over here. So let's shade that in. If you're less than 8, you're over on the left. If you're greater than 16, you're over here. So what is the area there for that two-part region, right? So the region is basically the tails there on the left. Well, what do we know about 95%? 95% is the area in between, right? So if 95% is this red area, how much is left for the blue area on the outside? Well, 100% minus 95% is 5%. So 5% of your population is going to be less than 8 or greater than 16. And this is going to be approximate, right? Because most populations aren't perfect normal distributions. If it's a perfect normal distribution, then these numbers are actually exactly correct, or nearly exactly correct. Anyway, let's see here. Approximately 99.7% of the values will be between what two values? Okay, so that's also quite easy to answer. 99.7 falls between 3 standard deviations of the mean on both sides, right? So it's sitting right in front of us. That's why I like to write out the segmentation, right? So 99.7 of the population will be between 6 and 18. What do you guys think? So could we do this with GeoGebra? Yeah, we could. Okay, but it's actually quite common to use this, because if you have a population, you want to break it up into groups. This is kind of a nice number of groups, right? I mean, how many groups do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So yeah, if you split your population up into 8 groups, that's actually a pretty good number of groups to work with. If you split it up into like 20 groups, that might be too many. If you split it up into 3 or 4, that might be too few. So, 7 or 8, segments actually is pretty easy and kind of common sense, I think, to work with. Okay, so let's do something a little bit more challenging, and it's going to require a little more work. And so on this next one, I'm going to do a little extra work. And At first, you'll wonder why I'm doing all this extra work because, well, we won't really need it at first, but later it'll become more useful for us. So let me do our segmentation again. This time we're back to doing quality control. So we're back to working at the plant again as some kind of quality control engineer. And now we're working on the machine that does corn chips. And so we're producing these 32-ounce bags of corn chips. The mean is 32.5. So that's our target. Notice they target it just a little bit higher than the advertised amount, which means they're careful about the quality. They don't want to go under their advertised amount. Standard deviation is 0.2 because, again, every machine, machines will do this, and even humans will do it too. You make a bunch of things, and they're going to be slightly different from each other. So as long as that slight difference is small, we're okay. And so here they're okay with the standard deviation of 0.2. So label the horizontal axis with the values of the 68, 95, 99.7 rule. So we're going to begin with the mean, which is 32.5, and then we add standard deviations from there. So that'll give us 32.7, 32.9, 33.1. Then we subtract 0.2. So that'll be 32.3, that'll be 32.1, that'll be 31.9. Okay, so what do we know about the first standard deviation in both directions? That'll pick us up 68%. So 68% of the data of the bags of chips will be between here. And that's great, but I'm going to take it a step further. I'm actually going to split that up into smaller pieces. Okay, so the 68% is equally split between the piece on the left and the piece on the right. So that means I have 34% in here and 34% in here. Does that make sense? 68 divided by 2 is 34%. And I'm going to actually continue doing that all the way down to the end of the distribution. Okay, so if I go 2 standard deviations out, I'm not going to pick up another 68%. There's not 68% left, but I will get up to 95, right? So 95 minus 68 is 27, right? So in this region and in this region added together, that's going to pick me up another 27% of the distribution. So that 27% is equally split between those two pieces. So just like I did with my 68%, I'm going to take that 27%, I'm going to cut it in half. That gives me 13.5. So that means I have 13.5% in here, 13.5% in there. So what's the point? Well, the point is I can answer questions more quickly later on, okay? All right, so that's 2 standard deviations. Let's go 3 standard deviations now. So I'm going to go 1 standard deviation, 2 standard deviations, 3 standard deviations to the right. And I'm going to go 1 standard deviation, 2 standard deviations, 3 standard deviations to the left. So now I'm picking up the middle 99.7%. There's not a lot left, right? There's just these 2 little pieces there, but there's still some in there. And so we want to account for that too. So how much more are we picking up? Well, we're going from 95 up to 99.7. So I'm picking up another 4.7% of the population. So 4.7% of the population lies in here or in there, right? So those 2 pieces are the same size. So just like I did with the other 2 numbers, I'm going to divide that in 2. And that tells me that I have 2.35% in here, 2.35% in there. Almost done. It's 99.7. That's not 100%, right? So it's almost 100%, but there's still a little bit left. How much is left? 0.3% is left in this little tail there and that little tail there. So 0.3, who cares? Well, you should care. I mean, it's a little bit of the population, right? So And it's, it's not like this is that, it's just arithmetic we're doing here, right? So that 0.3% is split into two pieces. So I'll divide that in two, and we get 0.15% over here and 0.15% over there. And we have it. We have our full segmentation. What is the value in doing that? Well, now we can answer these questions below much more quickly. So 68% will contain between what and what? Well, 68% is just one standard deviation, right? So it's going to be 32.3 and 32.7. That's easy enough. 95% will contain between what and what? Well, two standard deviations, right? So 32.1, 32.9. Okay. So you're still probably wondering why I went through with that full segmentation. Well, the next question I think will tell you, kind of, explain why we want to do that full segmentation. What percent would contain between 32.5? Okay, here's 32.5 and 32.9. Okay, so now it's just a little bit different, right? Okay, but if you see the two numbers up there, we can just say, well, there's 34% in the first part, and then there's 13.5% in the second part, for a total of 47.5. By the way, if you want, what you could have done is you could have just taken 95 and divided by 2, right? So there's multiple ways of getting to the right answer. I still like to have this segmentation drawn out like I've got like we did above here. Okay, so any questions there about that? Let's do one more. Okay, what percent would contain fewer or less than 32.3 ounces? So here's 32.3. And so for less than that, we're down in here. And notice we have all the segments right here, so we can just add them up. 0.15 plus 2.35 plus 13.5, and we have it 16%. The other nice thing about this segmentation is that except for the x-axis, all of these numbers remain the same. So here's what you can do. You can take a screenshot of this. I would exclude the x-axis because that does change every time. But this top part here is set in stone. So if you have yourself a formula card, you can just come over here and put it right there on your formula card. You've done right there. See? The numbers up top will not change. Those will be the same regardless of mu and standard deviation. Okay, so it was, it was a fair amount of work to begin with, but now the work is done. We can just write those numbers down and they don't change. And next time we do these problems, it's much easier. So in your notes, what you might want to do is just write those numbers down real quick. This is 34%. This is 13.5%. This is 2.35%. And this is 0.15%. The numbers on the left will be in the mirror image, right? So you might want to just put that on your formula card, something like that. And then those problems on the exam will be a cakewalk because you've got the segments already worked out. Okay, let's do one here. Let's talk about lifespans of refrigerators. Okay, so let's say you're an analyst or some kind of employee at one of these large electronics manufacturers companies, right? And you're trying to figure out what kind of warranty to offer on your refrigerators. How do they decide how much to charge for the warranty, and how do they decide how many they have to decide how much to charge for the warranty, and then they have to decide how long the warranty should last for, right? Does it last for 3 years? Does it last for 10 years? I promise you that they don't just like choose a number and go with it. They have a very good idea of the lifespan of their products. Okay, so So for this particular model, the mean is 14 years and the standard deviation is 2.5 years. So your typical refrigerator of this type will last 14 years. But you know how it works with products like that. Sometimes they just last a little bit longer or a lot longer than they're supposed to. Sometimes they go out early. So not every refrigerator is going to last exactly 14 years. And so that's reflected there in the standard deviation being 2.5. So I want you to use the 68, 95, 99.7 rule. I want you to turn off your GeoGebra. We're not going to do GeoGebra here. We could answer all these questions with GeoGebra, but I want you to practice with this rule. And we've got about 7 minutes here. I think you can make some good progress on this. So you're going to begin with the labeling, right? So you start 14 there, and then I'll do the first one. That would be 16.5, right? So do it all the way to the right, 3 standard deviations to the right, 3 standard deviations to the left. Then, if you're like me, what you'll do is you'll just put in the numbers from up top, right? 34, 13.5, 2.35, and 0.15. That's what I would do. If you want, you can drop in the dashed lines there. Okay. So I'll go quiet for about 3 minutes here, and then we'll come back together and talk about it, okay? All right, let's come together here a little bit. So I'm gonna keep adding 2.5, and then I keep subtracting 2.5. Okay. And then let's fill in these numbers. That'll be 34%, that'll be 13.5%, 2.35, and then 0.15. All right, does anybody have the first one? What percent of refrigerators have lifespans below 11.5 years? Anybody get that one for us? Let's see. Great. So 16%. Perfect. That's exactly right. So what do you do? Well, 11.5 is down here. So there is a substantial number of percentage of refrigerators who will go out below 11.5 years. It wouldn't be, unusual for that to happen, but it's not very likely either. It's about 16%. Okay. So pretty likely it'll last more than 11.5 years, but it could go out, right? So that might be a good place to put in a warranty. But again, it just kind of depends on costs, etc. So, okay, what percent of refrigerators have lifespans between 9 and 16.5 years? Anybody have that? Great, thank you. That's exactly right. Yeah, so you guys get the idea, right? So 9 years, 16.5 years. So if we shade that, and you'll be asked to do that quite a lot in this class. It's a bit of an exaggeration, but not much when I say that almost every problem for the rest of the semester will be using the normal distribution. Okay, so you'll be drawing this normal distribution and shading. So just get in the habit of it. Yep, 13.5% plus 34 plus 34 is 81.5. Okay, what percent of refrigerators have lifespans below 9 or more than 16.5? So below 9 or more than 16.5. So let's shade that. So that's this region down here, or more than 16.5, and then we have this larger region over there. Does anybody have that for us? We're getting a little bit low on time. Let me finish that. So less than 9 would be this 0.15 plus 2.35, and we have that larger region on the right, 13 plus 5 plus 2.35. I'm getting 18.5. Did anybody else get that? Great. And then what percent of refrigerators, these are like the gold star refrigerators, right? I mean, it just never dies on you. Imagine having a refrigerator for 21.5 years. That would be so awesome. Not very likely, right? It does happen, but like 2/10 of it percent of the time. Okay, before I forget to mention this rule is on your formula card. It's right here. Okay, so don't necessarily need to memorize those three numbers. Wouldn't hurt, but they are going to be there on your formula card. So on your homework, I mean, you can tell we're getting into this formula card. We're not super deep into it yet, but pretty much every day we'll be picking up something new from the formula card. So just print it off, have it with you in class, have it with you when you're doing homework, and definitely take this with you to the exams. Okay. All right, guys. Well, I'm all out of time for today. Are there any questions before we break? Anything you want to talk about real quick?
Where do we find the formula card again?
Yeah, it's on the home page. So let's see. So come over here to the home page, and then down below where it says formula cards, click on the formula cards. And I think probably the one you want to work with at this point is this version 1. Version 2 is basically the same thing, but it's just organized differently. So I think version 1 is probably what you want. Okay,
Thank you.
you bet. All right, guys, have a good one. Have a nice weekend. See you all back here on Tuesday.